All right, good morning. We are going to learn about scientific notation. Scientific notation is used to write either very, very small numbers or very, very large numbers. You have two key ideas. Make sure you write these in your journals. The first one is talking about scientific notation. A number is written in scientific notation when it is represented as the product of a factor and a power of 10. The factor must be at least 1 and less than 10. So when you see it, this is what scientific notation looks like. When you see it, this number in front has to be less than a 10, but at least a 1. So it can't be a 0 point something decimal. And then the power or exponent is an integer. And it can be either positive or negative. The negative means it's a very, very small number because it's less than 0. And a positive means it's becoming a larger number. There are two ways to write scientific notation back into standard or regular form. So if you see a number written in scientific notation, I'm just going to use the one you see up above, 8.3 times 10 to the negative 7. If the exponent is a negative, you're going to move the decimal point to the left. So I'm going to grab this decimal point and go to the left 7 times because that's what the exponent is. So I would end up getting 0.6 and then 7. And you just throw the 3 on the end. If it's a positive exponent, make sure you write this key idea in your journal. If it's a positive exponent, then you're going to move the decimal to the right. So say you have, 2.3 times 10 to the 6th. Since that's a positive exponent, you're going to take this decimal and you're going to move it to the right now, however many times. So you get 2, 3 is 1, 2, 3, 4, 5, 6. So then this would be the standard form of this number. Okay, so those would be your two standard forms. So negative, move the decimal to the left. Positive, move the decimal to the right. All right, so let's look at example 1. All right, put these in your journals. So for example 1, we're going to tell whether the number is written in scientific notation and then explain why, yes or no. So the first one, 5.9 times 10 to the negative 6. Well, you look at the number, the front number, the factor, 5.9. Is that between 1 and 10? Yes, it's greater than 1, and it is less than 10. And then look at the exponent, and is that an integer? And it is. So A would be, it is written in scientific notation. The factor is at least 1 and less than 10, and the power is an integer, so the number is written in scientific notation. So B, 0.9 times 10 to the 8th. First look at the factor. Is that greater than 1? Or at least 1, excuse me? No, it is less than 1. 0.9 is less than 1. So this is not going to be written in scientific notation. So you would say the factor is less than 1, so it's not scientific notation. All right, so let's look at the next example. All right, for this example, they have it written in scientific notation, and they would like you to write it in standard form. So you're turning it back into a regular large number or whatever. Now, this is example 2. Make sure you're writing it in your journal. So we have 3.22 times 10 to the negative 4. Write that down. And then look at the exponent. Is it positive or negative? This is negative, so which way are we going to move the decimal? To the left. So from that decimal point, right after the 3, you're going to grab it and move it to the left 4 times because that's how many times it says to move it in the exponent. So then you get your new number, 0.000322. So this is turning it into a very small number because it's a negative. So it's going very tiny into the decimal realm. So we moved it to the left 4 times. Okay, let's look at B. 7.9 times 10 to the fifth, written in standard form. So it's a positive exponent. So write 7.9 times 10 to the fifth equals, and then move the decimal where it's at. You see where it's at, and move it to the right 5 times. So that past the 9 would be 1, and then 4 more zeros. So 790,000. Okay? So positive exponent, we went to the right. Negative exponent, we went to the left. You just need to memorize that. But make sure you have it in your journal in case you forget. All right, so let's practice some on your own. All right, for the first one, let's look at this and decide, is this written in scientific notation? Well, the factor is 12, which is that at least a 1? Yes. Is it greater than 10? Yes. So this is not scientific notation because that factor has to be less than 10. So you would say no, and then because it's telling you to explain it, you say the factor is greater than 10. Greater than 10. All right, so let's do number 2. All right, here's number 2, 3, and 4. So we're writing the number in standard form for each of these. So first look at number 2. This is less than 10, great, and this is an integer, awesome. So we're gonna take the decimal. Where's the decimal in this whole number? It's right after the 6, right? It'd be like saying 6 point. And we're gonna move it to the right how many times? 7 times. So 1, 2, 3, 4, 5, 6, 7. So that means I'm gonna throw in 7 zeros here. So my answer, put a comma there and a comma there, is 60 billion. Okay. Number 3. We have 9.9 times 10 to the negative fifth. So which way am I going to move the decimal? 9.9, the decimal goes to the left. 1, 2, 3, 4, 5. Whoops, just 5. 1, 2, 3, 4, 5. So I'm going to have 2, 3. And the decimal goes there. So there's 4 zeros because the 9 is the first movement. Okay? And the last one, we have 1.285 times 10 to the fourth. This is greater than 1, 1.285. We're going to move the decimal 4 times, so 1.285. So each one of these counts as 1. 1, 2, 3, and I need to go one more, so I'm going to throw a 0 on the end. So 1, 2, 8, 5, 0. So 12,850. Not too bad, right? So positive, move it to the right. Negative, move it to the left. All right, let's look at example 3. All right, so example 3, write this in your journals. If you don't want to sketch everything out, that's fine. You just put page number. This is on page, whatever it is in your book. You might write out at least the measurements. The water is 1.0 times 10 to the third. The brick is 1.84 times 10 to the third. And the apple is 6.4 times 10 to the second. So an object with lesser density with water will float. An object with greater density than water will sink. Use each given density in kilograms per cubic meter to explain what happens when you place a brick and an apple in water. Well, you guys know well enough which one's going to float and which one's going to sink, but this is the scientific or mathematical way to know before you even put it in the water. So we're going to change each of these scientific notations into standard form because we have to find out whether the brick and the apple is greater than or less than the density of the water. So with water, you have 1.0 times 10 to the third positive, so we're going to move it to the right, which gives you 1,000. Because you move that decimal 3 times to the right, so you have 3 zeros. With a brick, 1.84 times 10 to the third. Again, you're going to move the decimal to the right 3 times. So that gives you 184, and then you need to throw another 0 on there because you need to move the decimal 3 times. 1, 2, 3. And then the apple, 6.41 times 10 to the 2. So again, you're going to move to the right because it's a positive integer. So grab that decimal, move it 2 times to the right, and you get 641. So looking at these 3 measurements, water is 1,000. The brick is obviously greater than 1,000, so it's going to sink, whereas the apple is less than 1,000, so it is going to float. So the apple is less dense than water, so it's going to float, and the brick is denser than water, so it will sink. Not too bad. All right. Let's look at example 4. All right, gross. We're talking about fleas. All right, so this is example 4. Put it in your journals. A dog has 100 female fleas. How many milliliters of blood do the fleas consume per day? So on the right-hand side, you see that a female flea consumes about 1.4 times 10 to the negative 5th liter of blood per day. So you see that it's a negative exponent, so there's a very small decimal here. So the first thing you're going to want to do is convert it to standard form. So you're going to rewrite 1.4 times 10 to the negative 5th. Oh, and they already wrote it out here that once you've converted it, we're going to multiply it times 100. So first step, they wrote the whole equation. Second step, you take that 1.4 and move the decimal. It's a negative exponent, so you're going to move the decimal to the left 5 times. So you see how we have 0.000014. Then you're going to multiply that number times 100. So basically, when you multiply it times 100, it moves the decimal back 2 spaces because there's 2 zeros. So you end up with 0.0014. So the flea consumes 0.0014 liter, or if I converted that to milliliters, it would be 1.4 milliliters of blood per day. And the reason you can say 1.4 milliliters is if you were to convert it, see how we're measuring this in liters over here? To change it to milliliters, you multiply it times 1,000. So then you would get the 1.4 milliliters. Okay? Since they asked for it in milliliters, make sure you check your measurements at the end. All right. Good. So now let's do on your own number 5. All right, this is talking back about example 3. What if, in example 3, the density of lead is 1.14 times 10 to the 4th kilograms per cubic meter? What happens when lead is placed in water? Well, remember, the water was 1,000 kilograms, right? So we need to see if this is less than or greater than 1,000. So 1.14 times 10 to the 4th. So I'm going to grab that decimal and move it to the right 4 times. So 1, 1, 4, that's 2, 3, 4. So you can see here that it is 11,400. So what happens? The lead is definitely going to sink. Good. Let's do the last on your own. All right, number 6, we're now talking about example 4 again, which was the fleas. If a dog has 75 female fleas, how many milliliters of blood do the fleas consume per day? Okay, so on this one, remember we had the flea consumed 1.4 times 10 to the negative 5th liters of blood per day. So the first thing we need to do is convert this into standard form. So we're going to move it to the left 5 times. So 1, 2, 3, 4. This is 5, and then 4. And then we're going to multiply that instead of times 100 like we did that last time. We're going to multiply it times 75. 0.000014 times 75 is going to give you 0.00105. Okay, so this is in liters so far, and we need to change it to milliliters. So then after you've done that, you need to multiply this number times 1,000. And all that does is move this decimal to the right 3 times. So you're going to have 1.05 milliliters, which is actually written like that. So this flea is going to consume 1.05 milliliters per day. Yippee. So don't let fleas stay on your dogs. All right, if you have any questions, please let me know. You have done the on your own, numbers 1 through 6. You need to do practice and problem solving numbers 3 through 23.